Okay, so the topic that we are going to cover today is corrosion, right? So when you think of when you think of corrosion, or when you hear of corrosion, you usually think of rust, right? That reddish brown color that metal usually get. Um, there's some sort of degradation. But actually, corrosion is a bit more than that, right? So rust is basically just a byproduct of corrosion. It's not what actually happens on a piece of metal. It's just the byproduct that tells us there's some corrosion happening. For some metal, when you have corrosion, there's no rust, so you can't really say that getting rusty is a sign of corrosion happening. Right? So, for example, in aluminum alloy, when you have corrosion, you don't get that reddish brown rust color. Okay, so first of all, why do we have to know about corrosion? Right? Because corrosion can cause failure that leads to like public safety and like health and safety, etc. Corrosion can cause a lot of loss, right, in terms of value of infrastructure. It's a waste, okay, and corrosion eats up metals, wasting time and money. About 3% of GDP in a developed country is spent concerning corrosion, whether it is indirect costs of repair, replace, the infrastructure or equipment that has been corroded, or indirect costs that has that's caused by corrosion. Like, for example, if there's a bridge that has corrosion problem and the bridge has to be closed for repair, then you have to take another route. You have to take a detour, and that will cause inconvenience and time as well, right? So 3% of GDP of a country, that's quite a lot of money, right? In Thailand, GDP of Thailand is about 1 trillion baht per year, I think. So 3% of that's that quite a lot of money. So that's why we have to know a little bit about corrosion so we can prevent it from happening. So we can like spend less money on corrosion or waste less money on corrosion. So that leads to the next question: what is corrosion? What is corrosion? Corrosion is basically an electrochemical process that involves oxidation reaction and reduction reactions. Okay? So to learn about corrosion, we have to understand what is an electrochemical process is. Right? Okay, so what is an electrochemical process? An electrochemical process is a chemical reaction that either causes or is caused by the movement of electrons. Okay, and an electrochemical process involves oxidation reaction and reduction reaction. Usually, they happen they happen at the same time, right? And sometimes we can call these uh, oxidation reaction and reduction reactions that happen at the same time redox reactions. Okay, a lot of the cases, these are just reversible reaction of each other, right? Some oxidation reaction will have a reversible reduction reaction, but for our purpose, this is not the case. Okay? Think about it. If we have an oxidation reaction of metal, in other words, metal loses electrons and become ions. Metal loses mass, right? And if we have the reversible reaction, which is the ion of that metal gaining electrons and then gaining mass. So if we have that reversible reaction, we wouldn't have any corrosion. Okay, because the forward reaction is the metal atom loses electrons, become metal ions, and the reverse reaction is the metal ions gaining electrons, become metal atoms. So you end up at the same place, so to speak. So you wouldn't have any loss of material or anything at all, right? In corrosion, usually the redox reaction that happens, they are not the same reaction, like going forward and backwards. Okay? And electrochemical process can be involved in a lot of things like power generation, corrosion, extractive metallurgy, how we refine metal ores into metals. Unfortunately, nearly all of our engineering metals are based on reactive metals. In other words, they cannot stay as pure metal. They usually react with the environment and form oxide, right? That's unfortunate because we want to use it in the metal form, in the metallic form, not the oxide form. But because they are reactive, especially to the environment, when we find them, they are usually in the oxide form, and we call that metal ores or mineral ores of different metals, right? Like magnetite, machimite for iron, bauxite for aluminum. Right? These are just the oxide form of the metals, and to use it, we have to refine it by removing that oxygen, right? To make the to transform the metal ores into pure metals, right? And that's what I mean by extractive metallurgy, right? So we're using usually heat and sometimes electricity to reduce that piece of metal ore, metal oxide, to pure metal, so that we can use it in our applications. Okay, so now we know that corrosion is just an electrochemical process, which is, in other words, a redox process, right? A redox reaction. So next we have a quick recap of what is a redox reaction, right? So a redox reaction is an electrochemical reaction involving oxidation and reduction reaction. Oxidation reaction is a chemical reaction when you have an increase in valence. Okay? For example, Fe turning into Fe2 plus, Fe2 plus turning into Fe3 plus. That's an increase in valence, right? And together with the increase in valence, we have a production of electrons. Okay, it's like iron or Fe turning into Fe2 plus, meaning it creating 2 electrons. Right, so the overall charge is the same. So you have 2 positive charge and 2 negative charge from the electrons. Right, so 2 positive charge from the iron, and 2 negative charge from the electron. So the overall charge is still neutral. Right, so oxidation reaction, you have an increase in valence, you have a production of electrons. Reduction reaction, it's just the opposite. You have a decrease in valence and you have a consumption of electrons. Okay, that's a mnemonic that to help you remember that when you think of redox reaction, think of an oil rig, right? Oil rig is that thing you see in the sea that like dig for oil and gas, right? So when you think of an oil rig, you can you can remind yourself that oxidation is loss, oil, and reduction is gain, right? Oxidation is loss of electrons, reduction is gain of electrons, right? So you know which reaction is which. Sometimes you will get confused between the two, which one loses electrons, which one gains electrons. Okay, so oxidation is loss of electrons, so you produce these electrons, so the atom itself loses the electrons. Okay, and the reduction is gaining of electrons. That means the ion the ion of that atom gain electrons and become different ions with lower valence, or become atom. Okay, so our main concern when we are talking about corrosion is the oxidation reaction, right? Because as you can see, the oxidation reaction that we are concerned with is the metal atom loses electrons and become metal ions. And when this happens, you have less and less of the metal atom. What that means is you have less and less mass of the material that you're starting on, right? So you have a loss of mass, and that is actually what happens during corrosion, right? So the corrosion that we are really concerned with is the loss of mass of our components. We're not really concerned with the rust that is happening. Okay, it might be unsightly, it might be a bit ugly, but it doesn't do anything to the overall integrity of the structure of the equipment. But the loss of mass will make our structure um, less strong, right? Because think about it, you start off with say 10, 10 centimeter diameter piece of steel, and you've lost some mass. That diameter becomes less and less. You get smaller diameter, so it can withstand less and less stress, right? So the reaction that we are really concerned about in corrosion is the oxidation of metals, right? So, for example, silver turning into silver iron plus electrons, zinc turning into zinc iron plus electron, or iron or chromium loses electrons, become ions or chromium ions. Okay? So, as you can see, electrons are produced by the oxidation reaction. And as a convention, oxidation reaction always occurs at anode. So when you find an oxidation reaction, we call that place where we can find oxidation reaction an anode, right? So the electrode that has the oxidation reaction is called an anode. It doesn't matter if it is a positive electrode or negative electrode. Okay, the positive and negative depending on the direction of the reaction. Say whether you are connecting it to a power supply or it is a spontaneous reaction. That positive electrode and negative electrode can change, but what cannot change is that oxidation always occurs at anode. So we call an electrode where there's oxidation reaction an anode. Okay, and there are many reduction reactions that can happen during corrosion. Right, the first one that can happen is the metal deposition. As you can see, it is basically just a reversible reaction of this reaction, right? So this is the metal dissolution reaction. Metals transform into iron plus electrons. And this first one is the metal deposition reaction. So the ion of the metal receives electrons, becomes metal atoms, right? And as I mentioned earlier, if we only have these two reactions, the metal dissolution and metal deposition, we wouldn't have any corrosion because the mass would be the same, right? So you lose this mass from the oxidation reaction, and then you gain the mass back by the reduction reaction. So we wouldn't get any corrosion, right? And that is true because although this is a possible reaction that can happen, it is really, really difficult to happen because, as I mentioned earlier, most metals that we use are reactive metals. That means it wants to give electrons and becomes ion and react with the environment, right? So the reversible reaction of that, which is this reaction here, is therefore really, really difficult to occur, right? This is much easier to occur. So the rate of this reaction is a lot faster than the rate of this reaction. So, we know that electrons are produced by the oxidation reaction, right? And that electron has to be used somewhere, or you have build-up of electrons. So there are other reduction reactions that can use those electrons, right? Depending on the condition. So if you have a strong deaerated acid, okay, so really, really strong acid, and you have no oxygen dissolved in that solution, you would get this reduction reaction. So basically, in strong acid, you have a lot of H plus or hydrogen ion or hydronium ion, right? So you have a lot of H plus there in strong acid. So you get the reduction of hydrogen ion into hydrogen gas, okay, in really strong acid because you have a lot of this. And in weak acid, weak and aerated acid, you have a reaction of oxygen and hydrogen ions, right? So both oxygen ion and hydrogen ion receive electrons and become water. Okay, so this is in weak aerated acid. And in neutral or basic solution, in other words, we don't have any H plus anymore, right? Unlike these two reactions. So we have the reduction reaction of oxygen and water turning into hydroxyl ions. Okay, so all these cover the whole range of the pH, right? So really strong acid, really, really low pH, and then you have like higher pH, and then you get to neutral and basic, which is more than pH more than 7, right? So this cover the whole range of pH, right? So really, really strong acid, pH maybe up to about 3, 4, right? And then you get this reaction here. And in weaker acid, you get this reaction here. And then in neutral reaction, you get this reaction. As the reduction reaction to go with this oxidation reaction, right? Don't forget, when we're talking about corrosion, we're talking about mainly this reaction here, right? So metal loses electrons, becomes metal ions, and those electrons have to be used somewhere, or you have build up electrons, you get a lot of electricity, and that is like not stable. So the system tries to reduce those number of electrons by inducing the reduction reaction. Okay, so the electrons are consumed by the reduction reaction. You can see all these electrons are consumed by the reduction reaction, and as a convention, reduction reaction always occurs at cathode. Okay, so now we know the basic. Corrosion is just an electrochemical process involving oxidation and reduction. Oxidation produces electrons, reduction uses electrons, etc. Oxidation of metal or metal dissolution causes the metal to lose mass, and that is the problem with engineering application because we use a lot of metals, and when the metal loses mass, it becomes weaker, right? It gets smaller, so it becomes weaker. Okay, so that's the basic of corrosion. And next we'll look at the basic corrosion cell. Okay, basic corrosion cell. So for all cases of corrosion, right, you will find all these four common denominators. Okay, so for all four components must be present in any corrosion cell. Right, so for corrosion to happen, you need all four of these. Right, so first of all, the most important one is the anodic reaction or oxidation reaction. In this case, is the iron loses electrons become iron and electrons. Right, so this is our oxidation reaction, and because oxidation occurs at the anode, so we can call this an anodic site, and we can call this half cell an anodic half cell. Okay? The electrons are then transferred to another site, and that induces the reduction reaction. Okay, so we have reduction of oxygen and hydrogen ion to become water. And this is a reduction reaction. It happened at the cathodic site. Okay. Okay, so you have anodic reaction, you have cathodic reaction, and the third one we just mentioned is the electron transfer. You have a movement of electrons. Okay, so basically you need a conduit for electron to move from the anodic site to the cathodic site. Usually, if it's in the same piece of metal, it will just move inside the metal. But in some cases, one piece of metal can be one electrode, another piece can be the other electrode. Like one piece can be anode, another piece can be cathode. So you need some sort of a connection between the two sides, right? We will look at those type of corrosion as well. Okay, so that's the third component. The last component is conducting electrolytes. Okay, so because we produce iron, so we need something that can support the iron, right? So we need an electrolyte, but it has to be conducting electrolyte, so it can support charged species like iron. Okay? Okay, so we need all four for corrosion to happen. So in fact, to prevent corrosion to happen, it is really easy. If you can get rid of any one of these from the equation, you've solved corrosion, right? Just any one of these. Doesn't have to be all of them, just one in the corrosion cell. But first you have to identify the corrosion cell, and then you have to identify what is the oxidation reaction in that cell, what is the reduction reaction in that cell, and how the electrons transfer between those two sites, and what is the conducting electrolyte in that cell, right? So when you can identify all those four, then you can get rid of like one of these, and then you solve corrosion, right? For example, if you just get rid of water, right? So you get rid of the conducting electrolyte, then corrosion is not going to happen, right? You can do that by coating it with a thin layer of oil to prevent water from sticking onto the surface. You are getting rid of the conducting electrolyte. That's it. You've solved corrosion. Okay. Okay. So that's the basic idea of corrosion. Right. So that's the principle of corrosion. So okay. Okay. So now we've learned about the basic idea of corrosion. Next, we will look at different types of corrosion. right? And all these types of corrosion will have the same four basic principles, right? But they will manifest themselves in different ways, and then that's the difficult part about corrosion. You have to identify all those four components so that you can control corrosion. Okay. The first type of corrosion that we're going to look at is called uniform corrosion, or sometimes called general corrosion. Okay? It is called general corrosion or uniform corrosion because corrosion occurs all over the surface, uniformly or generally, or all over the surface, right? So it's called general corrosion or uniform corrosion. Right? You have oxidation and reduction reaction occur uniformly all over the surface. Yes? And the byproduct, which is rust, is clearly visible. Okay. Okay. Talking about rust, let's go back to the previous slide. I didn't talk about it. Okay. So a product of the oxidation reaction is Fe2 plus, right? And when Fe2 plus reacts with oxygen, it will form Fe2O3 dot H2O, right? And that is the red rust that we get. Okay? And that is not the main product of corrosion. The main product of corrosion is Fe2 plus, right? So that can happen here. The rust can form here, or rust can form somewhere else. Depends whether the electrolyte is stagnant or it's flowing, right? So sometimes you can find rust downstream. Well, that doesn't mean like corrosion happens downstream. It can happen upstream, but the rust, the byproduct, occur downstream, right? So usually the rust formation is not a redox reaction. In other words, but there's no change in marks. Right? Okay, so next we'll look at the uniform corrosion. We have oxidation and reduction all over the surface. Because it happens uniformly, it's called uniform corrosion or general corrosion. Okay? This type of corrosion has little engineering significance because it is easily noticeable and it is easily fixed before you have any structural failure. Okay? And in some cases, like this picture here and this picture here, right? These are the fact that metals, especially steels, tend to corrode in humid environment. They use that to as an advantage. This building on the left here is the BBC Leeds building in Leeds in the UK. They are using a type of steel called weathering steel. The weathering steel react with the environment, it corroded, and it formed really reddish brown rust that stick really tightly to the surface to prevent further corrosion. So we know that it's got corrosion on it, and then it formed a really strong rust on the surface, and it gives this like reddish color to the building, right? They intentionally use that type of steel for this look, right? Leeds is in Yorkshire, in the north of England, and it's quite gloomy and cloudy almost all the time there. So the building, like with the reddish tints, sort of stand out in the grayish sky, right? This is the statue of the Angel of the North near Newcastle, in the northeast of England. they're using similar type of steel there, so that the angel of the north can be seen from the motorway and like in the reddish hue, like usually stand out from the grey cloudy sky quite clearly. But on that day it was quite sunny. So okay, anyway, so what are the causes of uniform corrosion? Okay, most engineering materials are reactive metals, and when they are used in the corrosive environment, they react. And when they react, you get general corrosion, right? So exposure to corrosive environment. Okay, corrosive environment is a very loose term to cover like really, well, what I mean to say is when you have humidity and maybe a bit of acidity as well, that would be even more corrosive. But if you have humidity and maybe heat, right, that can cause corrosion. That can be considered corrosive environment. Right? So basically, somewhere like Thailand, we are in a corrosive environment, okay, because temperature accelerates chemical reaction. So the higher the temperature, the faster the chemical reaction is, right? So in a humid and hot country like Thailand, corrosion can happen really, really fast. Okay. Okay, so we know that general corrosion occurs all over the surface, right? So to prevent corrosion, to prevent general corrosion to happen, we can use metal with passive film, like stainless steel, aluminum alloys, titanium alloys, etc. Right? So metals that can form passive film, like really, really thin film on the surface that can reduce corrosion by quite a lot. Okay, we'll come back to the corrosion protection later on, but for now, you will see a trend like for a lot of the protection against corrosion. We start with the metal with passive film like stainless steel, aluminum alloy, titanium alloys. Right? We can use painting or coating to cover the surface, so that way the electrolyte is not touching the surface, so we won't have any corrosion, right? So we are cutting out the conducting electrolyte from our equation. Okay, we can use inhibitors. Inhibitors are chemicals that can be added to the system to slow down the redox reactions. It can slow down. Some inhibitors can slow down oxidation reaction. Some inhibitors can slow down reduction reactions, and some inhibitors can slow down both these reactions. Right, and when you slow down either one of these reactions, either oxidation or reduction reaction, you slow down the overall reaction. Okay, we'll come back to that as well. The next type of protection we can use is cathodic protection. Cathodic protection is when we use something which is called sacrificial anode. Okay, so basically, if you want to make something protected against corrosion, you want to make that piece of metal a cathode, right? Because what happens at the cathode? Reduction reaction. Okay, that means you don't have any loss of mass by the oxidation reaction. If we make that thing that we want to protect a cathode, we call that a cathodic protection. We do that by using a sacrificial anode. We use a piece of metal that we can sacrifice in order to protect our metal, right? Okay, we'll come back to that as well, right, in corrosion protection. Okay, so That's the first type of corrosion. That's the most common type of corrosion that I'm sure you've seen, and that's what you think about when you think about corrosion, right? The next type of corrosion is called galvanic corrosion. Okay, I think you might have seen these before, but you might not know that this is a distinct type of corrosion from general corrosion. Okay? Galvanic corrosion is a corrosion that one component is preferentially is corroded to the other. So to have that preferential corrosion, that means you need two components, two metals, right? So the cause of galvanic corrosion is when you have two dissimilar metals in physical contact. The more anodic one will corrode. Okay? So in this case, in this picture here, you see a piece of stainless steel railing and a steel washer. Right? You can see the steel washer is getting corroded, whereas the stainless steel railing is intact. You have a lot of rust from the washer. Okay? The washer is more anodic than the stainless steel. Okay? So the washer is preferentially corroded, and you can see that the stainless steel pieces sets the stainless steel railing, and the bolt is not corroded at all. Okay? In this case, we have an aluminum nut and steel bolt. You can see that the steel bolt is totally corroded, but the stainless steel, this is the aluminum nut. It's still intact. Okay? So you have two dissimilar metal in physical contact. The one that is more anodic will be corroded. And how do you know which one is more anodic? We use something which is called a galvanic series. Okay? A galvanic series is a series that ranks the reactivity of metals and alloys in seawater. Okay, so this is this series is a series that's derived from experiments, right? So you basically you dump each of these metals in seawater and see which one corrodes more. And how do we know which one corrodes more? We use a mass loss test. We'll talk about that in corrosion measurement as well. So basically, the one that is more active, the one that is more anodic will corrode more, right? And we rank this by putting the more anodic one or the more active one down at the bottom of the table, and then we list it. The higher up the table, they are more cathodic or more inert. Okay? So when you have two dissimilar metals touching each other or in physical contact, the one that is lower down in the list will corrode away, leaving the one that is like higher up in the list. Okay, in this picture here, you can see the Statue of Liberty. The skin of the Statue of Liberty is made from copper and copper alloys, right? So it's quite higher up in the list, up here. But the structure, the structural framework inside, it's made from steel and cast iron. You have the bracing wire, right? And you can see that after like 100 years, the supporting frame has been corroded, and you have a looser fit in the copper rivets that rivet the skin to the framework. So if you follow the news, the Statue of Liberty was closed for a few years for repair, and it has been opened recently, a few years ago. Right? Yeah, it was closed for quite a few years. The reason it was closed because people could hear the statue squeaking when you have like high wind because you have lots of fits because of the corrosion of the framework, and some people could actually see the statue like swaying a little bit as well, right? And that is because of corrosion. The Statue of Liberty is located on an island, so you have the full exposure of the marine environment, which is full of chlorine, which is very, very corrosive. Okay? And without proper protection, you have a lot of like corrosion inside. The framework is made from iron and steel, right? Cast iron and steel, which is a lot lower than copper in the galvanic series. Okay. So the iron and steel will be corroded, right? So the framework is corroded, but the skin is still intact, right? After the initial patina. So initially, when it was cast, the statue had this coppery color on the surface, and then it's patina over time, right? So patina is a thin film, thin oxide film of that metal, in this case copper and bronze. So you start to get this like greening of the statue, right? Initially it was more coppery reddish brown color, and it gets more and more green over time. And it doesn't happen at the same time either. So some area might have like a patch of green forming, another area might still be like reddish brown, another area you have another like green area, etc. Until the green patina cover the whole surface, then you start to get uniform appearance. Okay, so the reason this type of corrosion is called galvanic corrosion is because of the galvanic series, this series here. And the reason this series is called galvanic series is because of an Italian scientist called Galvani. So they named this series to honor him. Right? He was an Italian scientist from a few hundred years ago, and he worked on electricity. So they sort of like named this series the galvanic series after him. Well, in chemistry, you might have seen the EMF series, right? Electromotive force series. You have the potential of that metal compared to the potential of this metal, etc. Those are not very useful in corrosion because those numbers, those electrode potential, is measured at the standard condition, right? The standard condition in this case means the metal has to be pure. That piece of metal has to be immersed in 1 molar solution of its own iron. It has to be measured at 25 degrees Celsius at 1 atmosphere of gas, right? In real life, we don't get that standard condition, right? Okay, for example, in most metals that we use in real life, they are not pure metal. They are mostly alloys, right? Alloys is a mixture. It's a solid solution of one element with another. For example, brass is an alloy of copper and zinc, right? Steel is an alloy of iron and carbon, right? So you don't get that electrode potential for alloys. because, well, first of all, we cannot control the solution to be like 1 molar solution of that alloy, right? It's really difficult. The ions react differently, but they're in alloys. Okay, so we use this galvanic series instead of the EMF series. It is more useful in terms of corrosion. Okay. Okay, so this is galvanic corrosion. In fact, I'll go to the next. I'll go to selective bleaching first, as we are talking about galvanic corrosion. Selective bleaching is basically a preferred corrosion of one element or constituent to the other. So, sounds familiar, right? So, galvanic corrosion is a preferential corrosion of one metal to the other, right? Selective bleaching is basically galvanic corrosion on the atomic scale, right? So for galvanic corrosion, you have, say in this example, you have copper alloys and the iron is lower than the copper, right? So the iron will be corroding, right? So you have two different type of metals in contact with each other. The one that is lower down in the list will be corroding, right? But for selective bleaching, it is happening in an alloy. For example, we are talking about brass, which is a copper alloy, right? Brass is an alloy of copper and zinc. And if we look at the galvanic series, we can see that zinc is way down here. Copper is way up here, right? So copper is a lot higher the galvanic series compared to zinc, right? But those atoms of copper and zinc mix together in this brass alloys. And the zinc atoms is preferentially corroded, leaving the copper atom in the alloys, right? And because the zinc is leached from the brass, it can be called de-zinkification, right? In fact, selective bleaching can be called de-alloying, right? Because alloying is an act when you mix two metals together to form a new mixture or alloys, right? Alloying is a mixture of two metals. De-alloying is when you are taking those two metals apart, right? Okay, so basically, selective bleaching or de-alloying is just a local galvanic cells in the atomic levels. Okay, if you look at this picture here, this is a piece of brass, right? So brass, you have copper, you have zinc. And if you look at the top bits, it looks really reddish, like coppery color, right? That is because zinc has been leached out from that area. And if you zoom in, you will see black area there, right? Black area in this top bit here, right? This black area is the area that has been de-zinkified. That means zinc has been leached out, right? So this black area, there used to be full of zinc atoms in here, okay? But all the zinc atoms have been corroded out, leaving this like empty space. But lower down here, you still have brass. Okay? You have brass here, you have copper here, right? Copper, but porous copper, full of holes. So the strength is not good, right? The strength is not good because one, it is copper. It is not brass. Like brass is stronger than copper. The whole idea of alloying is to make metals stronger, right? So copper is really, really soft. You put in a little bit of zinc in there, making it stronger, right? So when zinc is leached out, it's just pure copper again, so it is weak again. Not only that, it is very porous. It's full of holes, so it is even weaker than a solid piece of copper. Right? Okay, so selective leaching is a preferential leaching or preferential corrosion of one constituent or one element compared to the other. For example, zinc is leached from brass in a deacidification process, causes local galvanic cell. Zinc and copper are far apart in galvanic series. Protection, use low zinc brass. Okay, if we use brass with less than 15 weight percent zinc, this will not happen, right? Because when you have a small amount of brass, all those brass atoms, each individual brass atom is protected by the copper atom surrounding. You don't have any like exposed brass. I'm sorry, you don't have any exposed zinc atoms, right? So if you use brass with less than 50% zinc, all those zinc atoms are protected by the copper atoms. They are surrounded by the copper atom, so they cannot be leached out. Okay. Okay. So, or we can use if we have to use more than 15% zinc. In other words, we want an alloy that is stronger. We need more zinc in it. We add more zinc, and then we add arsenic as well, like 0.4% arsenic, to slow down the leaching process. Okay? It's not going to stop the leaching process completely, but it will slow it down considerably. Or we can use copper nickel alloys instead of brass, but in a little pricier. Okay. So if money is no object, copper nickel alloys is the way to go. Okay, so next type of corrosion is intergranular corrosion. Okay, intergranular corrosion. Inter means between, right? Like international means between nations. Granular is an adjective of grains. So intergranular means between the grains. Okay, so intergranular corrosion is the corrosion that happens along the grain boundaries or between the grains. Okay, so it is a corrosion along the grain boundaries. Okay. So if you look at this picture, you can see that corrosion goes nicely along the grain boundaries of the grains, right? The crack that is caused by corrosion goes along the grain boundaries. It doesn't go through the grain, it just goes along the grain boundaries. In this picture as well, you can see intergranular crack that is caused by intergranular corrosion. This is you can see corrosion between like the grains. Well, in this piece of material, this piece of material has been produced by the rolling process, and when you roll something, you squeeze it down, right? So initially the grain might be sort of spherical, but when you roll it between two rollers, you squeeze it down so the grains become really flat, like a pancake. And you can see that the grains sort of like, well, you can see the corrosion between the grains, and the grains are sort of like leaves or sheets of paper, right? Really thin. Okay. So this is also what you can see, like sort of layers. You can see layers like of grains, right? The corrosion goes between the layers of grains. Okay. Okay. So intergranular corrosion is corrosion of the grain boundaries. Causes special phases like chromium carbide, Cr23C6, that exists at grain boundaries causing local cavity. So this is a cause of intergranular corrosion in stainless steel. Right? In other materials, there are other special phases, right? So we're just taking an example from stainless steel, because stainless steel is one of the most widely used material that we know of, right? In aluminum alloys, you can have some second phase particles on the grain boundary as well, but we're not going to have to like remember all those. We just take this as an example. What happens in stainless steel and what happens in aluminum have the same mechanism. The difference is the second phase particle. The same thing in titanium alloy, magnesium alloy, whatever. Right? So in stainless steel, we have this phase which is called chromium carbide. Right? So it is an intermetallic compound of chromium and carbon. Okay, so how do we get to chromium carbide? So let's step back a little bit. So, okay, steel is the most widely used engineering metal in the world, right? In terms of tonnage. We use steel a lot because steel is quite strong. Okay, pure iron is not strong at all. It's quite weak. It's quite soft. It's very ductile. So we add a little bit of carbon inside pure iron. We change from iron to steel. Steel is much stronger than iron, right? Mechanically, it's really, really good, but it corrodes really, really easily. If you leave a piece of steel outside for a week, you will see plenty of rust on that piece of steel. Sometimes we need the aesthetic of no rust, so we choose a material that corrosion cannot happen easily. So we add in a little bit of chromium to that piece of steel, right? So we add at least 12% chromium to steel to make it stainless steel, right? Stainless steel means there's no stain, so there's no rust. Okay. In fact, in other language like German, right? They call stainless steel rostfree, which means rust-free, right? So it's basically the same thing as stainless. There's no stain, right? In French, Italian, Spanish, it's called inoxidable or inoxidable in Spanish, right? So I mean it's unoxidizable. So there's no oxidation. So there's no like rust basically. Okay, so we start off from iron, we add in a little bit of carbon, it becomes steel. We add at least 12% chromium so that it changes from steel to stainless steel. Okay? Okay. But we have carbon, we have chromium, and at high temperature, chromium and carbon wants to join together to form chromium carbon. Right? So if we use stainless steel at normal temperature, at room temperature, we would not get this intergranular corrosion. But if we use it at high temperature in this case means between 400 to 900 degrees Celsius, there's a chance that it will have intergranular corrosion. Okay, so you might think, well, we use stainless steel in everyday life, so there's no chance of getting. We use stainless steel in everyday life at room temperature, so there's no chance of getting intergranular corrosion at room temperature. Well, not quite, because during manufacturing of like everyday products, like the legs of this table here, they use welding, right? And welding process is a high temperature process. And during welding, the temperature of that piece of stainless steel can go up to about 500-600 degrees Celsius. And that is in the range where chromium carbide can form. Okay? So chromium carbide can form during welding. So basically, these chromium carbide particles form particles along the grain boundaries. Okay? And if you do a chemical analysis through the grains, right? So this is the grain boundary here, and this is inside the grain. You can see that you have 18% chromium inside the grain, and as soon as you hit the grain boundaries, you have chromium carbide, which has a lot higher chromium content, and then it goes down to 18% again, right? But you have the valleys here, right? These valleys is when you don't have any chromium, or you have chromium lower than the required 12%. Okay? Because the chromium in this area here will move to the grain boundaries to form chromium carbide. Right? So in this picture, you can see that you have chromium carbide particles along the grain boundaries, and inside the grain, just a short distance from the grain boundaries, we have this chromium depletion layer, right? Or chromium depletion zone, chromium depletion layer. So basically, this area here is this area here, the chromium depletion layer, right? That means you have lower chromium than the required 12%. And why do we require 12%? Because to form oxide film to cover the whole of the surface, to change from steel to stainless steel, we require at least 12% chromium. Okay? If we have less than 12% chromium, the oxide film that is formed is not going to cover the whole surface, and that is not going to be stainless. Okay, so we need at least 12% for our steel to become stainless steel. Okay, so even though we added 18%, and inside the grain, so somewhere around here, right, it's 18%. If we draw a line across the grain boundary, that's the line from here to here, right? So 18, 18, 18, you hit the grain boundaries, you have these valleys here. Okay? And then you get the peak of chromium carbide, and then you get the valley, and then the plateau of 18% inside the next grain. Okay, so when you have that, what happens is that now we have an area, that white area here, when you don't have any chromium, and this area when we have chromium, right? So if you look at the galvanic series, you have iron and steel, right? So basically, if you don't have chromium, your stainless steel is just a standard piece of steel. and compared to stainless steel active and stainless steel passive. Okay. So basically, basically you have galvanic cell of steel and stainless steel. The blue area is stainless steel, right? So you have a galvanic couple, a galvanic cell. So the white area is corroded preferentially. Moreover, the chromium carbide is also very cathodic, right? So you have high corrosion in the white area. Okay, so because of that, we have intergranular corrosion because the white area occurs along the grain boundaries. Okay, the white area is a chromium depletion zone. So to prevent this type of corrosion, you have to be careful when you are welding stainless steel. You have to control temperature carefully. You have to use careful welding technique. Okay, and you have to use low carbon in weld filler in electric arc welding, or you use electric arc welding. Use low carbon weld filler. Okay, so that you reduce the chance of forming chromium carbide. Quench the material after welding, or heat the entire thing up to 1,000 degrees Celsius, then quench. Quench in this case means just dump it in water, right? To cool it down really, really quickly. You heat it up above 900 degrees Celsius, so up to about 1,000 degrees Celsius, and then you dump it in water. Okay, so why would that help? Why would dunking it in water help? Basically, you cool it down really, really quickly so that the carbon atoms and the chromium atoms, they do not have time to join together to form chromium carbide. Because for them to join, they have to move to the grain boundaries and join together, right? And this is a process called diffusion. And for diffusion, you need time, okay? So at high temperature, those atoms have energy, and if you leave it at high temperature for a long time, they will have time to move to the grain boundaries to form chromium carbide. But if you dunk it in water, it will cool down really quickly. Those atoms will not have time to join together to form chromium carbide at the grain boundaries. Right? So quenching it will remove the time for the diffusion to happen. Okay, make the welded part thin. Okay, if you make the welded part thin, that will help in the cooling as well. Okay? So that means it will cool down faster. It will spend less time at high temperature, so there's less chance of chromium carbide forming. Okay, you can use low carbon content steel, for example, 304-ounce stainless steel, right? So stainless steel. Well, there are many grades. There are many types of stainless steel. Like a normal stainless steel that we would use, like in kitchen utensil or something like that, would be 304 stainless steel, right? It's got 18% chromium, 8% nickel, 304 stainless steel. But we have a low carbon version of 304, which is 304L, when L is denoting low carbon. Okay, so you have less than 0.03 weight percent carbon. So when you have less carbon, you have less chance of chromium carbide forming. Okay, or you can use stabilized steel. Okay, stabilized steel is just like something like a 304 stainless steel with extra alloying element like niobium, titanium, tantalum. added in, right? So it changes. The name change. The name changes from 304 to 347. Right? If you add these three alloys, okay. When you add these three alloys, they will when you add these three alloying elements, they will stabilize um, the the chromium carbide formation. So, in other words, these alloying elements can form carbide with carbon at higher temperature, and it will preferentially form niobium carbide or titanium carbide or tantalum carbide instead of chromium carbide. So you don't lose chromium uh, from along the grain boundaries. Okay, so next type of corrosion is crevice corrosion. So go back go back in the handout a little bit. Okay, so the next type of corrosion is crevice corrosion. Crevice corrosion is a corrosion that occurs in a crevice. A crevice is just a small gap. Right? So when you have two pieces of metal pressing against each other, you have small gap between the two pieces, whether it is a flat piece of steel or like in the spiral or in the flange area or underhead the rivets, underhead nuts and bolts, right? So you have small crevice or small gap between those two pieces of metals. And when you have small gaps between pieces of metals, you have something which is called differential aeration cell. Okay, so basically, differential aeration cell is just some sort of corrosion cell when you have different amount of oxygen between one area and the next. Okay, so imagine you have like a crevice here, right? So you have a small gap here, and you have a lot of water outside, some water inside. Where would you think we'll have more oxygen? Outside, obviously, right? Because inside you would have some oxygen, maybe the same amount of oxygen as the outside initially, but when those oxygen is used up, it would be difficult to replace oxygen inside the cracks, right? But the outside you have continuous supplies of oxygen all the time, so you have high amount of oxygen outside and very small amount of oxygen or no oxygen at all inside. And that is called the differential aeration cell. So basically, different amount of oxygen between the two areas. Okay? And when you have different amount of oxygen between the two areas, you have different electrochemical potential. Okay? So the more oxygen you have higher electrochemical potential. In other words, it is more cathodic, right? It is more inert. And lower in the if you have lower oxygen or no oxygen, it is lower down in the list. It is more active. So basically, now we get a corrosion type that has that have that have different amount of oxygen, and when okay, I'll talk about the mechanism after the next type of corrosion because they share the same mechanism. Well, anyway, so basically you have differential aeration cell, right? And that causes corrosion within the gaps within the crevice. Right? So you can see corrosion in the crevice, or corrosion in the thread of this bolt here, corrosion underneath the bolt, corrosion underneath the rivet heads. Okay, so protection against crevice corrosion, well, the easiest way is do not form crevice. Okay, so like for example, in this area here, we are using rivets to join these two pieces together, right? And when you join two pieces of metal using rivets, you get like gaps between the rivet heads and the metal sheets, or between the metal sheets itself. So if we use other joining technique like welding or bracing, we will not have this gap here. We just have a weld line. Okay? But bear in mind, if we are working with stainless steel, what would happen if we weld it? Because if we like if this component is made from stainless steel, what would happen if we weld it? We have to be careful of intergranular corrosion, right? If we use welding, because the temperature might be high enough that we get chromium carbide forming in or near the weld area, right? So we have to be careful about that as well. Or we can use sealants. We put silicone sealants inside this area to seal it, so that there won't be any liquid inside the gap. We can remove the stagnant area, so there's no standing water, right? So we can clean it, we wipe it down, wipe it dry, so there's no stagnant area of water. And we don't use any material that holds moisture, right? So basically, if you have something like a wet towel and you put it on a piece of metal, you leave it there, and for a few days you might get corrosion, and that is crevice corrosion because of you have some sort of like moisture, and the towel will act as a crevice former as well. So crevice corrosion doesn't have to happen between two pieces of metals, right? One piece can be metals, and the other piece can be um, other material like plastic that will not corrode. But if you have a gap between the metals and the plastic, water can go inside, and you can still have crevice corrosion. Okay? So I mentioned that because in galvanic corrosion, one way that we can prevent galvanic corrosion is by using inlet washer, right? So if we put an inlet washer between the bolts and the nuts, if you put the inlet washer between the stainless steel and this piece of steel here, you might prevent galvanic corrosion, but if you leave a gap between any of the metal pieces with the inner washer, you might still get crevice corrosion, right? So you have to really be careful when you're talking about different types of corrosion. When you prevent one type, you might cause another type. So you have to. That's why you have to know all these types of corrosion, so that you are aware that you, so that you are aware that you can prevent all these corrosion types. Okay, so this is crevice corrosion. Right? Next is pitting corrosion. Both crevice corrosion and pitting corrosion are known together as localized corrosion because it's corrosion in a specific area. Okay? But pitting is even more localized. Okay, pitting corrosion is even more localized because it is, well, if you look at the surface, it's just like a small dot. It's hardly noticeable at all, but it corrodes deep inside that piece of metal. If you look at this picture here, this is a cross section of a pit. You see an arrow here. If you look on the outside, you see a small pinprick, like really, really small, hardly noticeable. But when you do the cross section, you can see that the pits almost go through the whole piece of that material, right? It is really localized, and it is really difficult to be to notice. Okay, so that's why pitting is quite dangerous because it's difficult to detect, um, and also pitting is dangerous because usually pitting occurs to metals that we think do not corrode. Okay, I'll expand more on that. Okay, so pitting is a downward propagation of small pits, like in this picture here. You can see pits growing downwards, and you have like a big hole there on normally passive surface. Okay, okay. On normally passive surface, what I mean by normally passive surface is that, like I mentioned earlier, pitting occurs in metals that we think do not corrode, like stainless steel, titanium alloys, aluminum alloys. Those metals with passive thin film, right? Thin passive oxide film that usually prevent corrosion. Like stainless steel form this thin film, right? That prevent corrosion. And we think that, okay, we choose stainless steel because we don't want corrosion to happen. And we are using stainless steel so that we don't have to worry about corrosion. That is true regarding general corrosion, uniform corrosion, right? But stainless steel can still have pitting corrosion or surface corrosion happen. Right? So on passive surface, like stainless steel, okay? The cause of it is the loss of passivity, especially in presence of chloride. Right? The key word here is the presence of chloride. So marine environment, near the seaside, chloride-rich environment. Okay? Because chloride is very bad for passive film, especially passive film in stainless steel. Okay? So if you're using stainless steel near the sea, that stainless steel is almost not stainless at all. Like after a few years, you have to replace it, just like normal steel, right? Because the chlorine attack the stainless steel incessantly over time. The passivity sort of like disappears altogether, right? Okay, so to prevent or protect against pitting corrosion, material selection, we need better material, right? Like nickel alloy is better than stainless steel. It's more expensive, or stainless steel with a lot more nickel and molybdenum put in there, so that it can help against pitting corrosion. Solution conditioning, say if we want to use it, we have to get rid of the chloride in the solution. Or we can use cathodic protection, which I've mentioned earlier, when we use sacrificial anode, or anodic protection when we supply current directly to our component we want to protect. Inhibitors, chemicals that can retard corrosion reaction, or environmental exclusion, so we have an enclosure so that we exclude the environment altogether. Okay. Okay, so so okay, like I mentioned just now that pitting and crevice corrosion are localized corrosion. They are grouped together because they have very similar mechanism and they are very dangerous and difficult to detect. Pitting more so than crevice. Okay, for pitting corrosion to happen, you first start with pit initiation, right? The first step of pitting is pit initiation. So you start to get a small pit, and usually, if the original pit is small enough, the passive film can be reformed over the surface, and that pit will not grow. It will stop growing. So you get a small pit, and then a passive film cover it up. Nothing gonna happen, right? But stochastically speaking, statistically speaking, you might have like among 1,000 small pits, you might have just one pit that is just big enough for the pit to start growing. In other words, the film cannot grow, the passive film cannot grow fast enough to cover the whole surface of the pit. Like that, the pit is big enough to outgrow the growth of the film. And when you have that, you will start on the next stage of pitting, which is pit growth. Okay? And during pit growth, we have the same mechanism of pit growth and crevice growth. Right? So basically, this is inside a pit. This is inside a crevice. Right? So we have two pieces of metal joined together using a rivet. So you have this gap here, right? So zoom in this area. We have this gap between the two pieces of metal. So you can see that you have oxygen outside. There's no oxygen inside. This is a differential aeration cell. Inside you get metal dissolution, right? The metal transform into iron and then move out. Outside you have reduction reaction because you have oxygen outside. You don't have any oxygen inside, so you don't get any reduction reaction inside. So you get all the oxidation reaction inside the crevice and all the reduction reaction outside the crevice. Right? And when you do that, right? So all the metals are dissolved inside the crevice. The same thing happens in pitting as well. Right? So outside the crevice or outside the pit, we have reduction reaction. This reaction here happening here and happening outside the pits. Right? We have oxygen outside, so this reaction also occurs outside the pits. Inside the pits or inside the crevice, we have this reaction, which is metal dissolution. Metal transformed into iron plus electrons. And in the presence of chlorine, metals will join together with chlorine to form metal chloride. Right? And then usually metal chloride are quite soluble. So metal chloride will dissolve in water, turning into metal hydroxide and hydrochloric acid. Right? And hydrochloric acid will split into hydrogen ion and chloride ion. Right? And the chloride ion can go back and form metal chloride with new metal ion. Right? And when you have more hydrogen ion, it's become more acidic. Right? More hydrogen ion, the pH is getting lower. You get more acidity. You get more corrosion. So when you get more corrosion, it means you get more of this reaction here. So you get more metal ion. So the metal ion can form metal chloride with chloride ion, and these reactions can like sort of continue and um, continue inside, right? So this is what uh, was called a self-catalysis of um, self-catalysis of pitting and crevice corrosion, right? So it is self-catalyzing because as the one of the products of the process is acid, right? You get more acid, you get more acidity, and because you have higher acidity, you get more corrosion. And as you get more corrosion, you get more acid, right? You get more acid, you get more corrosion. So it keeps going round in loop, right? So that's why it's called self-catalysis of pitting and crevice corrosion. Okay? So that is one of the reasons why pitting you have this growth like this, because the further away from the pit already, you get like more acidity, and it's just like it will just dissolve metal deeper and deeper in this direction. Okay, selective bleaching. Okay, we've covered this. One thing that I've forgotten to mention is, you know, the dental amalgam, right? With the alloy that we use for filling in our teeth. The dental amalgam is a mixture of mercury and silver, copper, and zinc. Usually, when when you do a filling using the dental amalgam, usually they take a small liquid mercury and mix with like shavings of master alloy that is been mixed. There is a mixture of silver, copper, and a little bit of zinc, maybe a little bit of gold in there as well. You shave off a piece of that, like small shaving of it, and mix in equal weight to the mercury, liquid mercury, right? You mix it really well, and it becomes sort of like soft, like putty. You put it in the holes in the teeth to make the filling. So basically, you have a lot of metals in there, and in the oral cavity, you have saliva, so that's conducting electrolytes. So you could get selective leaching as well, right? From dental amalgam. And in some studies, they say that mercury can be leached out and can be detrimental to health, right? When when mercury is leached out from amalgam, but because we have so small amount of it, and there's no like conclusive evidence that it is really really bad, but um, well, nowadays you can have like different type of filling, right? You have resin, composite filling, etc. Okay, so intercranial corrosion. Okay, the next type of corrosion is called erosion corrosion. Erosion corrosion is just a combined effect of erosion and corrosion. Okay, so um, erosion is something that happens when you have flowing fluid, right? So when there's a fluid flowing, you will get erosion, right? So sort of like imagine a river with fast flowing water. The the side of the river will be eroded away, right? So that erosion, and together with the corrosive environment, you get this combination called erosion corrosion, right? So the combined effect has um, higher detrimental effect than each individual effect alone, right? It will it will cause failure much faster than corrosion alone or erosion alone. Okay, so it usually happens in bends in pipe when you have a change in flow, right? So like in this case here, when you have a flow direction from right to left, and then there's an elbow bend to change the flow direction. So you get like sort of turbulent flow here, and you get a lot of erosion here, and also you get corrosion as well. So you get this like hole forming in the elbow end. You see the surface here is corroded, and that's a big hole there. Here you have a burr or like roughness on the surface that is exaggerated because of erosion corrosion. So, and it's relatively clean because of the flowing fluid. So the corrosion product is not like deposited somewhere in particular, unlike rust, right? So if you don't have flowing liquid, the rust will stay in one place, and it will um, deposit at one place, and you will get uh, a pile of rust which is noticeable, right? But because it is flowing fluid, you don't see any rust, so it stays relatively clean, and you don't know about it until it is a bit too late when you have a big hole in your pipe. Okay, so causes combination of aggressive chemical environment and high velocity fluid flow. Okay, so basically you have high flow and corrosive environment. Uh, when you have a flowing solution, usually it will remove the passive film, right? So even though we are using stainless steel, the film on the stainless steel might not be permanent, right? It can be removed by the flow, okay? Because the film on stainless steel or aluminum alloy or titanium alloy, they are not static. The film is alive, right? So the film is getting sort of destroyed and rebuilt all the time, okay? So the film is getting destroyed and rebuilt all the time. We call this repassivation, right? But because of the fast flowing fluid, the film cannot repassivate the surface. So the film gets destroyed, but there's no new film forming on the surface. Okay, because of the fast flowing solution, right? The protective film is removed. Okay, so to prevent or protect against erosion corrosion, use erosion resistant material. So what are erosion resistant material? So basically, erosion is some sort of wear and tear, right? So what sort of property that we would select against wear and tear of material? Hardness. Okay, hardness is the ability of the material to resist change on the surface. Okay, so hardness is the ability of a material to resist plastic deformation on the surface. Right. So if a material is hard, the surface cannot be changed easily. That means it cannot be worn down easily. Okay, so the harder material is better. The harder material is more erosion resistant, Uh, and if we want to do the strengthening method, the best strengthening method for material used in erosion application is solid solution strengthening, right? So basically alloying, you put in alloying element to form solid solution, like you put in zinc to copper to form brass, that is called solid solution, right? It's better than second phase strengthening like precipitation strengthening, right? Um, which I'm pretty sure John Krishna has already talked about different types of strengthening mechanism as well, right? So solid solution strengthening is better than second phase particle strengthening when we are talking about corrosion, right? Use better design, right? So if you want to change the flow direction, the top picture here is a bad design, right? The lower picture is a better design. You can see that you have sharp bends, okay? So you get a lot of turbulence flow or really fast, really disturbed flow, right? Especially in the red area here, right? So this is the danger zone for erosion corrosion. When you have the change in flow direction, when you have the change in the diameter of the pipe, right? So you will change in flow rate, you will change in flow velocity, right? So if you want to change flow direction and like flow velocity, you should use a sort of like gentle slope, right, to change the flow direction like this compared to this. And to change the diameter of the pipe, you have a taper pipe instead of like abruptly changing the diameter, right? So the flow will be smoother and you will have less erosion. Change environment, in this case, for example, you can slow down the flow by using wider diameter pipe, right? So you would get the same flow rate, but you will have lower flow velocity, okay? Or you can use filters to filter out like particles in your fluid, because if you have particles like grains of sand in that, it will be more erosive, okay? Um, you can use electrochemical protection like cathodic protection, anodic protection, which will go into detail. Okay, this picture, this is the cross section of the wall of a pipe. You can see big holes, right? That is caused by erosion corrosion. So if you have oxide film on the surface and you have a surface anomalies like small holes here on the surface, you will also have a small hole on the oxide film, and that will cause the flow to change. Okay, from laminar flow, which is like orderly flow, you start to get turbulent flow. You can see that the film getting thinner, and you would go down to the metal, and you will get erosion and corrosion happening at the same time, and you get bigger holes, and you will eventually end up with something like this on the surface. Okay, so this is erosion corrosion. Okay, so next type of corrosion is called stress corrosion cracking. Okay, so it is a combination of stress and corrosion, right? Stress in this case is tensile stress. Okay, so you have uh, aggressive environment and tensile stress, and tensile stress can be either applied stress or residual stress. It doesn't matter as long as it is tensile stress, right? So basically, if you look at this picture here, you have a crack here, right? And if you have a tensile force or tensile stress, it will try to open up that crack, right? So so you need tensile stress to open up the crack, and when the crack is open, you would get like corrosion deeper in the crack. So you get a combined action of both corrosion and crack opening by the tensile force. So the crack will grow faster. Okay, and usually you have higher crack density as you go deeper and deeper. Okay, um, and there's some like specific environments and material that uh, you have to know about so that you can choose the best material for that environment. For example, uh, brass brass do not suffer from stress corrosion cracking in chloride environment. So brass is really good in chloride environment, like marine environment, in seawater. Brass is really good because it doesn't um, it doesn't corrode by stress corrosion cracking. That's why brass is used as propeller for like ships, boats, etc. But stainless steels don't do well in chloride environment. But conversely, stainless steel do not suffer in ammonia-rich environment. But brass cannot stand ammonia at all, right? Okay, so well, we look at different combination. All right, so aluminum alloys aluminum alloys don't do well in chlorine and seawater. Stainless steel don't do well in halines, or group 7, right? Chlorine, fluoride, bromine, iodide. Those are called halines. Neutral halines, hot halines, uh, concentrated concentrated caustic above 120 degrees Celsius. So uh, caustic soda at high temperature, etc. Ferritic stainless steel, ammonium nitrate and chloride, ammonium nitrate, ammonium chloride, hypochlorite. Hypochlorite is the stuff that you put in your swimming pool, right? So if you have a swimming pool and you have like pool furniture, you should you should choose the pool furniture that is made from austenitic stainless steel, not ferritic stainless steel, right? Because uh, austenitic stainless steel is much more resistant to hypochlorite than ferritic stainless steel. Carbon ferritic steel, or basically carbon steel, you have caustic sodium hydroxide solution greater than 50 degrees Celsius, calcium, ammonium, and sodium nitrate solution, seawater, etc. Nickel and chrome chloride above 200 degrees Celsius or low pH with oxidizer. Monel, which is a super alloy, so hydrofluoric acid, which is really, really strong acid. But Monel can withstand almost all any other acid apart from HF. Brass, we've talked about that, ammonia vapor and ammonium salts. Titanium don't do well with organic solvents. methanol. So, say if some of you might have, I don't know, like phone that's made from titanium, right? So sometimes you want to clean it. If you want to clean your phone that's made from titanium or wristwatches, don't use any organic solvent, right? Because it will make the titanium oxide film weaker and can be more easily attacked. Okay, so you just use warm soapy water, just clean it up just like that. Right? So organic solvent not a good idea to use with titanium alloy. Methanol, methanol or isopropanol, right? Not a good idea at all. So even even though you think like maybe the alcohol spray that you use to spray to this as a disinfectant to use to clean your hand, not good with titanium, right? Okay, so protection against stress corrosion cracking, remove or reduce stress, right? For example, if you have a lot of residual stress, you can do stress relief anneal. So basically, you heat it up and leave it to cool down slowly, so that you will get rid of all the residual stress. Or if it is an applied stress, you just reduce the stress. Okay. Use thicker section so that the true stress that the component is experiencing is lower, right? Change environment by adding inhibitors. Change material, right? So get better material for the given environment. So you have to think about the environment, like what sort of environment that material is going to be using in. Like, is it ammonia rich? Is it chloride rich, etc. So you have to choose the correct material. Use cathodic protection. So in this picture, you can see some sort of like wire connecting like one area to another, and you can see like a piece of metal there as well sticking to the pipe. This is called cathodic protection when you use sacrificial anode to prevent corrosion of the pipeline. Okay, so next type of corrosion is called fretting corrosion. Okay, so again, you might have noticed a trend here for the last 3, 4 type of corrosion. It is a combination of corrosion and other stuff, right? So for fretting corrosion, it is a combined action of aggressive environment, i.e. corrosion, and small amplitude motion. So basically, it is a rubbing action, right? So the stress is normal to the surface, causing rubbing action. There's a wear scar, like in this scissor here, resulting in looser fits or seizure of component, or it can be the initiation of fatigue cracks. Right, so you can see that this piece of metal is getting thinner here, so you have lots of fits around here. Right, so this is fretting corrosion when you have combination of fretting, which is just like rubbing together, and corrosion. It can be a problem in ball bearing as well. It can cause either loss of fit or sometimes it can cause seizure, right? So if you have a lot of corrosion product, it can cause seizure. So the ball bearing, the bearings do not move, right? The ball bearing like doesn't move as it should, right? So it doesn't move freely anymore because of the seizure of the ball bearings and the corrosion products. Okay, so fretting corrosion is caused by a high normal load between two surfaces, and you have relative motion between two surfaces, right? So you have high normal load and relative motion in this direction. So basically, you are rubbing on the surface, and the surface is relatively quite rough, even though it looks smooth to our eyes. But the surface asperities in the like microscopic levels, they are like sort of like really rough, and that will cause the fretting to occur, right? So you have the fretting action, the rubbing action on the surface, and you have the aggressive environment. So that will cause um, fretting corrosion, right? So the fretting can occur in the wear oxidation mechanism or oxidation wear mechanism, right? So wear oxidation means you have rubbing together, you're causing wear debris, small pieces of metal that comes out after wearing down the surface, and those debris get oxidized, so you get like really hard oxidized metal trapped within the two surfaces and keep rubbing on the surface, so you get more and more fretting corrosion. Or you get another type of fretting corrosion is called oxidation wear. So the surface gets oxidized, so you have oxide film on the surface. And the thing about oxide is that it is really hard but brittle. So when you push the surface together and rub them together, this oxide film on the surface will break. So you get a lot of small but really hard oxide between the two faces of between the two surfaces, and they will rub on the surface and will cause more and more wear. Right? So it can be wear oxidation or oxidation wear, depending on the type of metal we're talking about. Right? Protection against fretting corrosion. So the first one is easy. Reduce the normal load. So if you're pressing the surface together with less force, you would get less wear. Okay, you will get less rubbing action. You get less wear. So you reduce fretting corrosion. You can also reduce wear by lubricate the two surfaces, or you can use harder material. You can do that by increase the hardness by solution hardening, or change material. Okay. Use gaskets or sealants so that you can prevent corrosion on the surface, right? So you don't have any like electrolyte between the surface. You should avoid material that oxidize easily and form tenacious oxide like titanium, aluminum, right? Those are materials that are oxidized easily. So basically, if you are rubbing on the surface, the wear debris get oxidized very easily, and the wear debris are oxide. They are really hard and they keep rubbing on the surface, right? So titanium alloys, aluminum alloy are at risk of fretting corrosion if you are having this like rubbing on the surface. Right? Okay, next type of corrosion is corrosion fatigue. Right, so a couple of weeks ago we've covered fatigue, right? And I've told you that fatigue is the cause of about 90% of mechanical failure, right? And in that 90%, I think about 15% is corrosion fatigue. Okay? So corrosion fatigue is quite a big cause of failure in engineering application. Okay, so we call cause on fatigue, right? So what is it? So it is a combination of aggressive environment and cyclic stress. Because when we have cyclic stress, we get fatigue. Right? We have cyclic stress or dynamic stress or fluctuating stress, we get fatigue. Okay? And when we get fatigue and we add aggressive environment to fatigue, we get corrosion fatigue. Okay, and if you have a look at this SN curve, stress amplitude and number of cycles to failure, right? So this is a schematic diagram showing SN curve of a material, right? So if you are testing the uh, fatigue life of a material in air, in water, or in sodium chloride solution, you would get different SN curves. This is the same material, right? So in air, you might get a fatigue limit. Okay, you might get a fatigue limit. That means if you're using it with the stress amplitude of less than this fatigue limit, you will not get fatigue. Right? It will not fail because of fatigue. But when you are testing it or you are using it in water, you can see that the SN curve shifts to the left and shifts down. Okay, and it shifts to the left and shifts down even more in sodium chloride solution. Right? That means the fatigue life and fatigue strength decreases. Okay, so the number of cycles to failure decreases. Okay, when we compare fatigue life with no corrosion is present. Okay, in other words, in an aggressive environment, decrease the life of the component. Right, so you can see from the SN curve that aggressive environment decrease the life. Right, so say if we use this stress amplitude here, right? So in air, it will not fatigue, right? So you can draw a line like from here. Draw a line parallel to the x-axis. You will not get fatigue if you use it in air because it doesn't intersect with the SN curve of in air, right? It will intersect with the water line here. So it will fail somewhere around this amount of number of cycles. In sodium chloride, it will fail somewhere around here, right? So the more aggressive environment, the shorter the fatigue life. Okay. The reason for that is because the corrosive environment reduces the crack initiation stage by introducing alternative mechanisms. So in fatigue, we have two stages of fatigue, right? We have fatigue crack initiation and fatigue crack growth. In fatigue crack initiation, if there's no corrosive environment, basically you need a crack to form, and that crack will start to grow, right? And that crack will form by mechanical means only if you don't have any corrosive environment. And it can take between 50 to about 50 to 75% of the life of the fatigue life of that component, like 50 to 75% of the fatigue life. So it will take a long time for fatigue initiation, fatigue crack initiation to happen, right? And then once that happens, it will start to grow in fatigue crack growth, right? But in aggressive environment, it doesn't have to depend only on mechanical means like persistent slip band joining together, dislocation joining together to form crack on the surface. It doesn't have to depend on that only, right? Crack initiation can happen because of corrosion as well. You can have pitting corrosion on the surface, and then you have a small pit. That pit can act as a fatigue crack initiation point, right? And fatigue crack growth can grow from that pit. Okay, so pitting can act as the initiation stage for fatigue, and then it can grow by the fatigue method. Okay, so the first stage, the crack initiation, it doesn't have to be by mechanical mean only. By mechanical mean only, it can be by electrochemical as well, like fatigue, like galvanic corrosion, like many other different methods, right? So, and in the second stage, which is the fatigue crack growth, corrosive environment produces a faster crack propagation rate. So the crack growth rate is faster when you have corrosive environment, right? Because you have the corrosive or aggressive environment, it will corrode inside the crack as well. So it will make the crack grow faster. Okay? But the striations will be sort of flatter. Okay? So the striation, which is in this picture here, if you zoom in on the fatigue crack fracture surface, you will see these striations. These lines representing a step that a crack grows, right? It grows, stop, grows, stop, grows, stop. Each step that it grows and stop, you get this one line here. Okay? If there's no corrosive environment, you can see really sharp line. But if you have corrosive environment, so when the crack grows by one step, aggressive environment comes in and corrode all the sharp lines, all the peaks of the striation, right? So the striation looks flatter, almost like cleavage-like. Okay, so that's what you see on the fracture surface of fatigue, corrosion fatigue. Okay, so apart from the crack growth by the fluctuating stress, you get general corrosion at the crack tip to make the crack bigger as well. The crack length increases from mechanical stress as well as corrosion at the crack tip, right? So you have two factors that make the crack grow, right? Mechanical factors, fluctuating stress, and also corrosion at the crack tip, so it grow much faster. Okay, corrosive environment oxidizes the metal surface quickly when the crack opens up. Okay, so when the metal is oxidized, you have oxide film on the surface. So when it closes down again, remember we're talking about fluctuating stress, right? So we have crack opening, crack closing all the time. Right? But when the crack is open, you have oxidation and you have oxide film forming. And when the crack is closed, there's no re-welding or rejoining of the crack tip. Okay, if there's no oxidation of the crack tip, you get some sort of forge joining, forge welding effect, right? Basically, like when you're pressing two pieces of metal together at high force, you can join those two pieces together. This is called forge welding, right? So basically, when you open up the crack, it oxidizes, and there's oxide film on the surface. So when you close it, they are not two pieces of metals anymore. So they cannot join together by welding. Okay, so the crack tip is prevented from re-welding, and also you get wedging effect by the corrosion products. So you get corrosion products, oxide inside the crack, right? So when you close it, you have the oxide product inside there that prevents the crack to completely close. Striation become fatter, okay. Protection against corrosion fatigue, okay. Reduce stress by thicker section, better design, eliminate cyclic stresses, stress concentrations. Okay, so better design, right? So choose material with low fatigue crack propagation rates. In other words, the second stage, right, which has about 25 to 50% of the fatigue life of the material, right? Uh, so if it has low fatigue crack propagation, the life will be like longer. Material can withstand fatigue by two methods. The first is resist initiation but have a rapid growth. Okay, we don't want that. The second, allow easy crack initiation but have a slow crack growth rate. For corrosion fatigue resistance, the second is the better material, as in corrosion fatigue crack initiation is accelerated by other methods like pitting already, right? So we want it to grow really slowly because the first stage, it doesn't, the pit initiation stage is not controlled by mechanical means anymore. It's controlled by electrochemical means. So the mechanical properties of that material is irrelevant, right? In the first stage of fatigue, which is fatigue crack initiation. But fatigue crack growth, on the other hand, you still have two distinct mechanisms. You have fatigue crack growth by the fluctuating stress, and also fatigue crack growth by the corrosion, by the aggressive environment, right? So you want a material that is resistant to fatigue crack growth mechanically, so that that portion of the crack growth will be like lower, right? Induce compressive stress on the surface, like shock heating, carburizing, etc. So basically the same with fatigue that we talked about 2 weeks ago, right? So compressive stress on the surface, making the mean stress lower. We can use catalytic protection to protect against corrosion, use inhibitor, use coating, organic coating, inorganic coating, etc. Okay, so those are different types of corrosion. Next, we will look at corrosion testing. All right, so the first one is a simple test called salt spray test. Right, salt spray test is basically you have a test chamber. You put in multiple samples inside the test chamber, and then you spray all these samples with simulated seawater, which is a salt solution with about 5% sodium chloride. Right, seawater has about 1.8 to 3% weight percent sodium chloride. So this simulated seawater, 5% sodium chloride is even more aggressive than seawater. And depending on the standard that we are following, sometimes the salt spray will be sprayed continuously all the time. Sometimes it will be periodic, right? Like so, you have like a period of wet and dry cycle, okay? Depending on the standard that you are following. You put the sample in the test chamber. You spray salt spray on it. And then after a certain period of time, you take it out, you analyze it. Okay, and you analyze it into two key ways, right? You do it qualitatively and quantitatively. Qualitatively is basically just look at it. What happens? Are there any corrosion products visible on the surface? Is the size visibly smaller, bigger, etc.? You do it qualitatively, right? And also you do it quantitatively. In other words, you measure the mass of that piece of material before you start the experiment. You put it in the test chamber. After a certain period of time, you take it out, you measure the mass again, and see how much mass has been lost by the experiment. So you can calculate the corrosion rates, right, by the mass loss technique. Okay, so you use a mass loss technique to calculate the corrosion rates quantitatively, and you can describe the result qualitatively as well, right? Like in this picture here, you can see that after 48 hours, this electrogalvanized carbon steel begins to have white rust on the surface. whereas the AISI 441 type stainless steel doesn't change at all. There's nothing on the surface. And after 380 hours, you start to get red rust on the surface as well. You still have white rust, but there's more red rust forming on the surface of this carbon steel. But the stainless steel still unchanged, right? So that's the sort of um, qualitative result that we're looking at. Usually, you have to put the samples in there for quite a long time. Like in the automotive industry, the standard is about at least 1,000 hours, right? So quite a long time. Okay? It takes quite a long time, but it is considered an accelerated testing because of the simulated seawater and the wet dry cycle. It will take short time, relatively, of about 1,000 to 2,000 hours compared to the exposure or exposure testing where you put the sample outdoor, and you measure the weight loss over like a year, over 5 years. That would take much longer time, right? So this is an accelerated testing, even though it takes 1,000 hours, right? A few months, more or less, right? So it's faster than a few years. But if you are short for time, we are you can use an electrochemical testing technique, which takes maybe 10 minutes, half an hour, like maybe 1 hour, including setup and cleaning afterwards. Okay, so an electrochemical testing techniques. Basically, you are setting up a corrosion cell, right? So your sample would be the working electrode and the WE. The reference electrode is an electrode that you measure the potential of your working electrode against, and the counter electrode is to complete the circuit, right? So if your working electrode becomes the cathode, the counter electrode will be the anode, and if your working electrode becomes the anode, the counter electrode will become the cathode, right? So it basically complements the working electrode, right? So sometimes you might see the counter electrode for auxiliary electrode, right? Auxiliary means like to help. Counter electrode means opposite of the working electrode, right? So if the working electrode is a cathode, the counter electrode is the anode, right? So you put all the three electrodes in a cell, you put the solution in there, plug it into this potential stat. This machine is called a potential stat. That machine control potential and measure current, etc. So, and then you get a graph of potential and current. You manipulate the data a little bit. You get corrosion rates from that quite quickly. Right? Okay, so next, we will look at corrosion control, right? So if you recall, when in this class, all the corrosion protection, corrosion prevention, control, we've talked about all this, like nearly on all types of corrosion. Right? The first one is using a self-protecting metal, using a self-protecting metals like metals that can form oxide, like stainless steel, aluminum alloys, titanium alloys. Okay, so these metals, when they are oxidized, they form a thin, passive oxide film. Right? The film is really thin, in the range of about 10 nanometers, right? 10 nanometers, really, really thin, like not visible by naked eye. So human hair is about 50 to 100 micrometer, right? this film is 10 nanometer, so that, well, so say if human hair is 100 micrometer or 100 micron, this film is 10 nanometer, so that the film is about one 10,000th of the human hair, right? Really, really thin. And the film is clear, so you can't really see the film. But the film is there, and it will slow down corrosion rate by about 1 billion times, right? So notice that I use the word slow down the corrosion rate. It doesn't stop the corrosion rate. That means stainless steel that we use doesn't stop corrosion. Corrosion still occurs, but at a much slower rate, about 100,000 times to 1 million times slower, right? When you compare stainless steel and normal steel in the same condition. Okay, so the metals combine with oxygen to form a thin adhering oxide layer. So this is the metal oxide film on top of the metal that will slow corrosion. Okay. Okay, so we know that in chemistry, temperature can increase the rate of chemical reaction, right? So if we reduce temperature, we will slow the rate or slow the kinetics of both the oxidation reaction and the reduction reaction. In other words, it will slow down corrosion if we can reduce the temperature, right? Okay, inhibitors are chemicals that we add to the corrosion cell to slow down the corrosion rate, right? So there are two main types of inhibitors. We have cathodic inhibitors and anodic inhibitors. Cathodic inhibitors are inhibitors that work on the cathode and slow down the reduction reaction. Anodic inhibitors are the inhibitors that works on the anode and slow down the oxidation reaction. Okay, so some inhibitors work by slowing down both reactions, but most inhibitors work by slowing down either reaction, either oxidation or either reduction. Okay, so inhibitors slow down oxidation reduction reactions by removing reactants. For example, removing oxygen gas by reacting it with an inhibitors. Okay, so this type of inhibitors is called oxygen scavenger, right? So basically, you add the oxygen scavenger inside your system, and that inhibitor or that oxygen scavenger will react to the resolved oxygen until it uses up all the oxygen that is dissolved in the solution. So there's no more oxygen to react in the redox reaction, right? So that will slow down the reaction. Another way that the inhibitors can act is by, well, it can slow oxidation reaction by attaching species to the surface, like similar to painting the surface, but these are usually vapor phase inhibitors, right? So for vapor phase inhibitor needs to be used in enclosed space like oil tank container, etc. Or in a contained space. So the vapor phase inhibitor, when you add in that, it will become vapor and it will attach itself to the surface and cover the surface so that humidity and moisture doesn't come near the surface, right? So it will slow down corrosion in that way. Similar to painting, when you paint the whole surface so that moisture cannot touch the surface. Okay, cathodic or sacrificial protection, right? Cathodic protection or sacrificial protection, they are the same thing. Right? So basically, cathodic protection is a type of corrosion protection when we use a more anodic material to the ones to be protected. Okay. So basically, we make the component that we want to protect a cathode. Okay, that's why it's called cathodic protection. We try to protect the cathode. Cathode mean what? Means uh, reduction reaction, right? So in other words, no oxidation reaction on the piece of metal that we want to protect. Okay, so if we want to make our component the cathode, we have to provide another type of material that is more anodic, so that that piece of material can become anode, can oxidize and send electron to the cathode to protect the cathode. For example, this oil pipeline here that is made from steel is protected by a piece of magnesium. Right? So if you look in the galvanic series, magnesium is way down in the galvanic series. So magnesium is going to corrode preferentially to steel, right? Even though those two pieces are not physically in contact, we can provide a copper wire to join the two pieces together. So the magnesium electrode can be corroded and send electrons to protect the steel pipe. Okay? So this is cathodic protection of the steel pipeline by magnesium armor. Another type of cathodic protection that is more common, you might have seen this without knowing it, when you see corrugated roofs. There are zinc-coated steel corrugated roof, right? So basically, you have thin sheet of steel, and then you just dip it in molten zinc. So you get a small, really thin layer of zinc coating on the surface of steel. And zinc is lower in the galvanic series compared to steel, so zinc will corrode preferentially to steel, right? But because of zinc on the surface, we will react to carbon dioxide in the air to form zinc carbonate, which is almost like a passive film, passive layer, right? So it will protect zinc from corrosion unless you have like mildly acidic rain, which will wash off that zinc carbonate layer, and then zinc will corrode, and then after zinc has been totally corroded, our piece of steel will be corroded. Okay, so that is protection of steel uh, by providing barrier layer to steel by adding zinc and zinc carbonate. Okay, that's one way of protecting that piece of steel. Another way, right, is when the zinc is scratched. Okay, so if there's a scratch on this piece of material, so that bare steel is exposed. Okay, when bare steel is exposed, you would expect steel to be corroded as well, right? But no, because zinc is lower down in the galvanic series, so zinc will be corroded preferentially, sending electron to steels, and steel becomes cathode. So there won't be any corrosion of steel until all the zinc has been corroded away. Then you would get corrosion of steel. Okay? So even though there's a scratch through the zinc layer exposing bare steel, you won't get any corrosion of the steel until all the zinc is gone. Okay, so that corrosion control. Okay, so corrosion summary. Corrosion occurs due to the natural tendency of metals to give up electrons. Entering metals are usually reactive metals. They want to give up electrons and react with the environment. The electrons are given up by an oxidation reaction, and these electrons then are part of the reduction reaction. The galvanic series ranks the reactivities of metals in seawater. Increasing temperature speeds up oxidation and reduction reactions. So we can control corrosion by reducing temperature. We can use metal which form a protective oxide layer. We can add inhibitors, which are chemicals that retard oxidation reactions or reduction reactions. We can paint it, or we can use cathodic protection. Okay.